All right, so here's 2.2, which I'm going to title Mass Spec and the AMU. First of all, let's take a look at what this mass spec stuff is. If I were you guys, I'd be asking this question. How do we know the percent abundance of the isotopes in these elements? You had that hafnium problem on the lab, and it said if you had 200 atoms, 10 of them would be hafnium-176. That's like, what, 5% of the atoms are 176. Well, how do we know that? We can't grab onto atoms, and we can't count them individually. So there's got to be some type of machine or detector that we use, and, well, in comes along something called the mass spectrometer, which uses the concept of mass spectrometry to find the percent abundance of isotopes. And so this is how it works. So you take an element, right, and you vaporize it. All that means is that you turn it into a gas. So you get it super hot and you turn it into a gas. And then what you do is the machine itself is going to ionize the sample. Okay, so what that means is it's going to give the sample either a positive or a negative charge. And to do this, it's either going to add or remove electrons from the sample. So if it adds electrons, then the sample is going to become positively charged. And if it removes electrons, then the sample will become, if it adds electrons, it'll become negatively charged. And if it removes electrons, it'll become positively charged. Next, the sample is going to be passed through an electrically charged tube. So you'll now have an ionized sample, which will have a charge, passing through an electrically charged tube. And here's what happens. If the sample contains two different isotopes, one with a high mass and one with a low mass, the isotope with the low mass is going to deflect a lot. Okay, and so we can see that in my image that I've got right here. We can see the low mass sample is deflecting really, really greatly away from the original trajectory of the sample. And the original trajectory I'm going to outline here in green. So there's the original trajectory. On the other hand, if it's a high mass sample, then we're not going to get as much of a deflection. Okay, so let's highlight that in like yellow. There's the deflection right there. All right, so we can think of the high mass being, let's say, hafnium. That's an H. There we go. I'm getting a little. There we go. Hafnium 180. And we can think of the low mass sample as being, I don't know, hafnium. Let's call that hafnium 176. Okay. And so the detector will pick up the percentage of the isotopes that are being spit at it. And you think about this, like if we had all of us line up in the hallway, and I was rolling down a super heavy bowling ball and a tennis ball, and I had you like kick at the balls. And if you kick the bowling ball, it would deflect, but it just wouldn't deflect very much. Okay, that's the high mass. If you kick the tennis ball, it's going to like ricochet over to the other wall real quick, right? And so that's what we use. We use this mass spectrometer with ionized gases to try to detect the percent abundance of isotopes in an element. All right, so let's move on to the second part then of this lecture, which is going to be the understanding of the units for average atomic mass. Now, once again, if you're looking at a periodic table, the average atomic mass is going to be denoted in each symbol, and that's going to be the number that's not a whole number. So remember, this number right here, that's the atomic number, and that equals, this guy right here equals the number of protons. We're not talking about that right now. We're not talking about that guy. We are talking about the 32.07 in the case of sulfur, which is the average atomic mass. Now, with every unit in science, we always have, or with every number in science, we have a unit that's associated with it. So it's interesting to think about the units for average atomic mass. Normally, we use grams in science for mass. Okay? Now, you're probably more familiar with the idea of pounds when you talk about like how much something weighs. But actually, if you lived in Canada or Europe, you would never work with pounds. You would not even probably know your weight in pounds. Somebody would ask you for maybe how much you weighed or what your mass is, and you would know what that is in kilograms. If you have a loose understanding of what a gram is, it's just the fact that you've been born in the United States and have lived here your whole life. If you lived in Europe or Canada, or even in the Middle East or in Asia, you would have a different concept of that, and you'd really understand grams. But most of the time, grams are going to be used for mass. Now, atoms, as we know, are so incredibly small that grams just aren't convenient because we say, well, how many grams is an atom? That number is so small, it's got so many zeros to the right of the decimal point that it's just a pain in the butt to write. So we come up with a new unit. We define something called the atomic mass unit, which is abbreviated, as you all know, as AMU. So the atomic mass unit is defined as being the mass of one nucleon. Right, so now you think, okay, what's a nucleon? Well, a nucleon is just simply a proton or a neutron. Now, believe it or not, protons and neutrons have very, very similar masses. The neutron's a little bit bigger, but not enough for us to worry about. So, in essence, we say the proton and the neutron have the same exact mass. And that mass is equal to one atomic mass unit. So, for instance, carbon-12. Carbon-12 has an atomic mass of 12 AMUs. And this should make sense, because if you think of carbon-12, carbon, every single isotope ever for carbon has 6 protons. And in this case, this isotope has 6 neutrons. So 6 plus 6, that's 6 AMUs for the protons and 6 AMUs for the neutrons. You add them together, and so the mass here is 12. But let's remember that the mass on the periodic table is an average. So the 32.07, that's right here on my slide, is an average. It's a weighted average of all the isotopes of sulfur, so hence the decimal place, right? Yeah, okay. All right, so let's do a little bit more work with AMUs on the next slide. Many of you are probably thinking, okay, so we're using this thing called AMU, but what does that really mean? What's its relationship to grams? Well, both AMU and grams measure mass. Let's get that out of the way. But the relationship between the two is an interesting thing to take a look at. 1 AMU is equivalent to 1.66 times 10 to the negative 24th grams. Okay? What I've just written there is called an equivalency. And you're familiar with these. I could say, oh, I don't know, 1 dozen is equivalent to 12 things. That's an equivalency, all right? So this isn't anything new, I don't think. You should be able to understand what an equivalency is, all right? So if we want to convert between AMU and grams, we have to be able to use this equivalency to our benefit. Okay, so for instance, if I said, oh, an atom weighs 19.00 AMU, and someone's curious and says, well, how many grams is that? We have to be able to do that conversion. So we're going to use things called conversion factors in order to give us this answer. And I'm going to show you what the 2 conversion factors are right now for this particular equivalency. Whenever you have an equivalency, so that means that there's this little equal sign in between the 2 values, you can always change that equivalency into 2 conversion factors. All right, here's the first one. We can say that there's 1 AMU per 1.66 times 10 to the negative 24th grams. Okay, so this is like a division bar right there. Okay, so your 1 AMU are on top, and 1.66 times 10 to the negative 24th grams are on the bottom. All right, so that's the first one that we can use. The second thing that we can say is we can actually take what's called the reciprocal of that. We can flip that around. So the other conversion factor is simply 1.66 times 10 to the negative 24th grams over 1 AMU. Okay, so we have here 2 conversion factors. Now, we're going to have to pick one of those 2 when we ask the question, okay, we've got so many AMUs and we want to turn that into grams. And I'll show you how to do that on the next slide. All right, so let's go there now. So let's go with that sulfur atom that we were talking about before. So let's say we have 32.07 AMUs, and we want to know what is that equal to in grams. Okay, so let's set that up. Well, the only number that I have given to me in the problem is this number right here, is the 32.07. So I know I'm going to probably have to work with that. Okay, so I'm just going to rearrange, and I'm going to write, or I'm not rearranging, I'm just going to write that number down here. 32.07 AMU. Now, if you look at your notes, we had, let's see, we had a blue conversion factor and we had a purple conversion factor. We had 2 of them on the previous slide. Only one of them is going to help us answer this problem, okay? Now, here's the key. What we want, folks, what we want at the end of the day, we want this guy. We want grams. How many grams? So I always ask the students, think about what you want to be left with at the end of the day, all right? And when you think about that, you figure that out, take that unit and make sure that that's on the top of your conversion factor. All right, so we're going to do that. Now, if you look back on those previous conversion factors, the conversion factor that had grams on the top had the little tiny number up there too, 1.66 times 10 to the negative 24th. Now, we do not forget the denominator. We want the stuff in the bottom as well. And that was what? That was 1 AMU. There we go. All right, so what do we do from this point? Well, we got to go ahead and we got to cross out the AMUs. Okay? Whatever's on the top of your fraction, if you got something like on the top, and when I say on the top, think about this number here being over 1, because we can essentially put any number over 1. If you have a unit on the top of the fraction, like this dude is right there, and you got a unit on the bottom of a fraction, like that dude is right there, you can cross those units out. It's just like in math class. If you have like 4 over 2 times 1 over 4, you can cross out the 4s. It makes life a lot easier. Okay, so what do we do from this point now? Well, it's just like multiplying fractions. You multiply the numerators, that's the 32.07 times 1.66 e to the negative 24th, and your calculator spits out a number for you. Okay, and that number in this case is going to be what? It's going to be 5, let's see, it equals 5.32 times 10 to the negative 23rd, and then we need a unit, right? Because this is science class, and we always have units, and remember, your units is right there, and that's grams. That's a G. All right, so that's your unit. All right, so this video is a little bit longer, and especially when you do some of the Ed puzzle questions, might take you somewhere about 15 minutes, but thanks for hanging out with me.